Hi, welcome to this module, and in this module what we will learn? We will learn how to design and build a temperature controlled circuit using operation amplifier as an on off controller and proportional controller. So, how can we develop a temperature control circuit? So, now where exactly you find this kind of circuit? You find this kind of circuit in many applications. So, let us see how we can design this circuit, and then we will see what application we have thought of. So, to start with, if you see the slide, the temperature controller is a process of maintaining or controlling the temperature of a system to a specified value by continuously assessing the current temperature of the system and adjusting the system parameters in order to meet the user requirements. So, what we can see, it can be used for air conditioning system, it can be used for AHUs, it can be used for in industry applications. A lot of applications are there for temperature control circuits. Now, in particular industries, temperature monitoring is very important, and when you talk about research laboratories, it is as equally important like industries in a research laboratories as well. So, when you talk about pharmaceutical industry or you talk about food industry, a temperature control is extremely vital, is extremely important, right. So, how to design a temperature control system? So, the first idea that comes to our mind is to use a simple closed loop system, but it is very important to understand the effect of requirements of a system before we actually implement it, right. So, a simple and low cost control used is on off controller, which merely uses switches the heater either on or off when the temperature rises or falls below the threshold as per the design. So, the easiest way to design is to design a on off controller. So, but in that case the what happens, this makes the system to continuously switches on and off, right. In on and off controller what happens, the system continuously switches between on and off state. So, when you see that what you see in the slide, you see that when you do that, the actual temperature of the is calculated as the average of overshoot and undershoot of the temperature. A much more expensive method is by changing the input bias on the error by calculating difference between the required temperature and actual temperature. If you know the required temperature, if you know the actual temperature, then you can understand the difference and minimize the overshoot or undershoot depending on how complex we can use the controllers or how complex controllers we can use. So, now the aim of this particular experiment is, the major task is to control and maintain temperature on the plant, right, as per the user requirement. This is our aim one. This requires a plant which generates heat. One way is designing a plant as heating source using transistor which produces heat because of high power, right. Second is the control action needed to be bring the temperature to desired set point, which will be obtained by designing a basic controllers with an objective of minimizing error for settling. Now, what are our objectives? The objectives are, first is to implement a circuit for heating of the transistor, and second objective is to implement a controller to maintain the temperature of transistor, right. So, let us see how we can do that. Now, this is a block diagram of the closed loop control system, where you can see the system input is given to the error detector, and the based on the system input and the feedback signal, finally whatever the error is there, that is fed to the controller, right, which is further manipulated by and you can assume that a variable ut is applied to the heating plant, right. Based on that, either the circuit will heat or it will shut down, that is on or off, and the temperature at the output is measured, which is again fed back to the sensor and signal conditioning circuit. That means the sensor and signal conditioning circuit consists of the temperature sensor, right. And if the temperature is higher than what is the set point, right, then that kind of feedback signal is given, and if the temperature is lower, then according to that the feedback is given to the error detector. So, the point is our error should be minimized, that is the idea, correct. So, now what is the role of error detector? Error detector produces an error signal, which is the difference between the input and the feedback signal. This feedback signal is obtained from blocks which are feedback elements by considering the output of overall system as an input to this block, correct. So, instead of direct input, the error signal is applied as an input to the controller, right. Instead of directly we apply system input, we apply the error, that is the difference between system input and the feedback signal. Now, what your controller consists of? Your controller consists of, or it actually the system which produces an actuating signal which controls the plant. The combination, the output of the control system is adjusted automatically till we get the desired response, right. And hence the closed loop control system are also called the, or also called as the automatic control systems, right. So, we can also call it is a closed loop system, or we can also call as an automatic control system, right. This is very easy. Now, the implementation of error detector, that is the measures the difference between input and the feedback signal, as we have discussed, right. As error amplifier experimental procedure, you see this is the circuit. Okay. So, what we have to do, connect V1 and V2 such that V1 equals to V2 to input of the error amplifier, right. So, if V1 equals to V2 and that is sent to the input of the error amplifier, correct. Now, measure the output voltage VO, this is your common mode operation, right. Now, connect V1. So, let us do the second part, and second part what we do, and actually we will see this thing also in the experiment. Okay. We will see in the experiment class how to design this particular temperature controller circuit. So, the second one, second part of this experiment is connect the V1 to high signal and V2 to a signal which is low and measure the output. If there is a difference, right. So, there is a differential mode gain, and finally, you can calculate CMRR and a differential gain of the system. You know that CMRR is nothing but the ratio of differential gain to common mode gain, right. Now, for sensor signal conditioning circuit, how to implement that? For that we have the temperature of the plant, that is the amount of heat dissipated of the transistor. Let us consider as LM35 temperature sensor. So, we will use LM35 temperature sensor for implementing our signal conditioning circuits, and let us assume the sensitivity of the input is 1 volt per degree centigrade, that is our sensitivity. Okay. Now, the sensitivity of LM35 is 10 millivolt per degree centigrade. Now, from where we get this LM35 is 10 millivolt per degree centigrade, we can get from the data sheet. The scaling factor of the input and sensor should match in order to perform the error calculation. Thus, the signal conditioning circuit is required for sensor with a gain of 10, right. You can see that sensor output and the input, right, scaling factor should match, and for that in this particular condition we require an amplifier or a signal conditioning circuit with a gain of 10. Now, for the error amplifier procedure, what we will do, we will connect the circuit as shown in figure 1, or this particular figure. Let us assume this is figure, not figure number 1, just a figure. Okay. Now, connect 1 volt as an input to the system, right, that is at sensor output here 1 volt, and measure the output at VO1 here and VO, and what you have to do, you have to calculate the gain and phase of the system. Now, for implementing or implementation of heating circuit or plant, it is a simple circuit for converting voltage to current. The circuit contains a feedback loop through op amp that keeps voltage across the resistor R1 constant, and thus a constant current, right. This is the circuit. The current flow in the transistor is depending on the input voltage, right, because whether transistor is on or off depends on what is the voltage that we apply, what is the voltage that we apply to this operational amplifier, right. Now, due to this feedback, the power across transistor is high, initiating the transistor to heat, right, or we can see the heat dissipation in the data sheet. So, designing of this circuit would be the voltage drop across R1 will be nothing but equal to V1. Now, if IE equals to, IE is your current flowing through ammeter, is equal to IR1, right, is equal to, you can say IE is equal to IR1. Now, what is IR1? IR1 is V1 by R1, right, V1 by R1, or you can say it equals to alpha times IC, which is the current through the collector. Now, drop across transistor is nothing but V 2 minus V 1, V 2 minus V 1, alright. So, that will be the drop across the transistor. So, for heating circuit experimental procedure is you can connect the circuit as shown in figure, which is right over here, and apply a DC input voltage V 1, right, 0.5 volts, and we slowly increase the voltage at steps of 0.5 volts, and for that we observe the output current I out and calculate the relation between output current and input voltage. That is a procedure for the experimental part. Now, let us see two position on off controller. Here what we see is again this is the same thing, it is a hysteresis control, the compressor or speed and refrigerated transport system. There is a ambient condition that we have to take in picture, and then there is a carbo space temperature. This is a feedback given to the error. Like I said that this is a set point on at which we want to have the temperature of the system, and whatever the error is there, based on that the error is fed to the hysteretic control. Now, this is another example where you can see the two position control system, right over here, and this is the plot where we can see that what is our set point, right, what is the designed or designated value, and what is the hysteresis differential, right. At the same time, how the temperature controller will work. It will switch on and switch off when it is above set point, right, above set point you can see here it switches off, when it goes below set point here it switches on. So, this on off action is continuous whenever the set point the temperature is below the set point or above the set point, we can start or we can work on the on off control action of the circuit, right. So, if you go to the next slide, what we find that if you want to implement this on off controller, then the basic and simplest form of controller, this is on off controller, or basic and simplest form, very easy to design. The output will be either on or off, and there is no middle state. The state of the output depends on thresholds which are decided by resistors and reference. This is also called Schmitt trigger. We have seen Schmitt trigger circuit earlier as well. Like I said, we have seen Schmitt trigger which is inverting Schmitt trigger. We have seen Schmitt trigger which are non-inverting Schmitt trigger. So, now if you consider R1, R2 and R3 as resistors as shown in figure, which is right over here, right, R1, R2 and R3, and if we apply Kirchhoff current law, which is KCL at node V1 here, right here, then what do we get? We get I1, this current flowing to R2 is equals to I2 plus I3, right. So, now if we substitute value of I is V by R. So, I1 is V plus, right, minus V1 by R2 equals to what is our I2? I2 is nothing but V1 which is voltage over here, right, and it is here. So, V1 by R1 plus what is I3? I3 is V1 here, right. Now, we have output voltage VO. So, there is a difference here. So, V1 minus VO1 divided by R3, correct. So, if we equate this, then what we have? We have V1 equals to R equivalent by R3 VO1 plus R equivalent by R1 into V plus. So, how to perform this particular experiment, or what is the procedure, experimental procedure for implementing error amplifier? Then the first thing is you have to connect the circuit as shown in figure, which is right over here, and then connect sinusoidal input to inverting terminal of the operation amplifier, which is your error input, and let us say it is 1 volt peak to peak, and or we can observe the output voltage VO1 at the output of the amplifier. Same way we can compare the theoretical thresholds with the practical threshold. So, we need to understand the how can we implement the error amplifier. Now, the next one would be signal conditioning for on off controller. So, how we can design signal conditioning circuit? So, first thing is the output of an on off controller triggers between V plus and V minus. Okay. So, the output of the on off controller triggers between V plus and V minus, we know that, right, because it is on and off state. Now, consider the maximum input applied to the plant is 1 volt. If I apply the maximum input of to the plant which is 1 volt, so hence to meet the requirement of the plant, a signal conditioning circuit should be used between controller and the plant, we also know that, correct. Now, signal conditioning circuit is used as an attenuator by simple logic called linearization. So, if you want to design a signal conditioning circuit, what we can do? We can consider R5, R6 resistors as shown here, which is right over here and right over here, right. And if you see, its gain is 1 by 15, 1 kilovolt, 100 kilo ohm, and is a 15 percentage, 1 by 15. The output voltage VO is VO1 into gain, which is 15 into 1 by 15. Right, and which is equal to 1. So, if you want to design the error amplifier, you can connect the circuit, apply DC input 15 volts, and then you can measure the output, compare the theoretical with practical threshold. This is similar to the last slide. Now, this is about on off controller. On off controller is kind of easy. Let us see a proportional control action. So, for a controller with proportional control action, the relationship between the output controller UT and attenuating error signal is given by UT is proportional to ET. Now, we know that, right. So, if I further solve this, then we can have UT equals to KPET, where KP can be a constant, and or in Laplace transform quantities we can write down US by ES equals to KP. KP is termed as a proportionality sensitivity or the gain. So, this proportionality sensitivity or the gain, we can keep it constant, we can change the gain, of course. So, we can say a proportional term where we use KPET. Okay. So, now, you see this in which we have this realization of proportional controller, right. So, you can see that there is a fulcrum, and as soon as the weight as soon as you open the valve, the water goes down and the fulcrum moves this side, helping the water to fill the tank, right. So, this is the kind of proportional controller. Same way in this case you understand this is A. Let us keep in the equation. If we keep in the equation, you can see here also very simple thing, narrow P band, wider P band, right. It is very easy to understand. And then you have here a proportional band which is all the way A, B, C, right. So, you have 3 things here. First one we have to understand is y equals to A by B, x, where x is a valve position. So, if I consider A here, B here and a valve position, so y, this y is here, this y is nothing but A by B into x. So, we can write y equals to kpx, right, where kp is nothing but A by B, or we can say y is proportional to x, right. So, it is very simple example, and it is beautifully shown in this particular slide. It is very easy to understand, right. You have this A, B and A, and you can see that offsets signal. As soon as it goes down, this will start filling up, and that depends on how you operate the valve. When the valve is closed, at the time the tank can be filled. When the valve is open, you can see the tank is getting emptied, right. And based on that, the fulcrum would help to open and close the valve from which the water can flow in. And the same thing we are kind of describing in this next figure, where we are showing as a and B, where the switching of valve is shown, which is like the entry of the water, and then the B side is where if you open this particular valve, then the B side would be higher than A, and thus we can when we solve this. So, this difference is nothing but y, right, and if you want to know y, then y is proportional to x, which is your proportional band, where y is proportional to x, and you can also write y is equals to kpx, where kp is nothing but A by B. So, continuing with our discussion of proportional control system, the critical properties of proportional system are how it computes the control effort. That is a very important parameter. The measured output is subtracted from the input to form an error signal, okay. And a controller exerts a control effort on the system being controlled. The control effort is proportional to the error given, and this name, that is why this method is called proportional controller, right. So, the equation ut equals to Kp into Et, where Kp is proportionality sensitivity or gain, and the like I said, the control effort of proportional controller or the control effort is proportional to the error given, and that is why, right. See, the control effort is proportional to the error given, and that is why this method is called a proportional controller. So, if I want to implement the proportional controller, what can I do? So, a simple gain amplifier is used as a proportional controller. The output proportionality changes based on the input signal, hence it has a linear relationship between input and output. The proportional constant is Kp, like we have discussed earlier, it is a constant. Design of Schmitt trigger. So, if I consider the resistors as shown in figure, right, I can design a Schmitt trigger very easily. The first op amp is for inverting of the error signal, and the second op amp is to set the gain, right. So, this one will help us to invert the signal, this one will help us to adjust the gain. The moreover, to meet the requirement of the plan, the second op amp will be used to attenuate the input. The gain of the system is nothing but VO by VO1, VO by VO1 equals to R6 by R5 equals to 1 by 10, right. R6 by R5 equals to 1 by 10, and if I set value of R6 equal to 1 K, right, or R5 equals to 100 K, alright. In that case, we can have 1 by 10, and the output voltage VO is VO1 into gain, which is 10 into 1 by 10, which is nothing but 1. Now, for experimental procedure is concerned, we can see that we can connect the circuit as shown in figure. We can connect 1 volt as input to the system, which is right over here, and measure the output voltage at VO1 and VO, and calculate the gain and phase of the system. So, this is how we can implement the experiment. Now, when you talk about proportional, how about proportional integral control action? So, for control with proportional and integral control action, or a controller that has both proportional and integral action, the relation between output controller ut and the actuating error signal Et is given as ut is proportional to Et and ut is proportional to integration of Et dt. So, ut equals to Kp into Et plus Kc into integration of Et dt. Now, if you put this thing in forms of Laplace quantities, then we can see that Us by Es equals to Kp plus Ki by S, where Kp is proportionality gain and Ki is our integral gain. So, if you have proportional integral controller, you can write the equations like this. Now, for realization of the integral controller, we can see that the proportional term considers the current size of Et only at the time of controller calculation, but the integral considers the history of the error. That is why the proportional integral controller are better than just a proportional controller, and there are other controllers called proportional integral derivative, which is PID controller, which are even more better than PI controller. But anyway, let us continue our integral controller right over here. So, the proportional term, like we discussed, considers only the current size of Et and while controlling calculation, but the integral considers also the history. So, how long and how far the measure process variable have been from the set point over a time, and that is very important for a controller action. Now, integration is the area under the curve, the integration of error over time, and is the summation of the complete error up to the present time. You can see here, right, what is the error, you can say the area under the curve. Same way, if there is exceeding our value, again the area of the curve, right. So, this will again in this case you can see the area under the curve. So, it is the integration of error time in the summation of complete error up to the present time, right. So, a plot which is right over here, right, and we are acknowledging controlguru.com because we have taken the plot from that particular website. So, a plot shown is an example of a controller error Et shaded with the integral sum. Now, the idea of our whole NPTEL platform is to help student for teaching, and that is why we kind of get the best of the images from possible sources, so that it is used only for teaching purpose. Okay. So, to compute the integral sum of error, count the number of boxes, we can do the counting number of boxes, and if the error is large, the integral mode will increment or decrement the controller output, and if the error is small, the changes will be slower. It is very simple. Now, for a given error, the speed of integral action is set by controller integral gain, right. For can be set by the controller integral gain. If the integral gain is set too small, the controller will be sluggish. If it is too large, the controller will oscillate and become unstable, correct. So, that is how thing stands, but if you want to implement the PI controller, which is proportional integral controller, then we know that this is nothing but a combination of proportional integral controller. Proportional controller can be implemented using gain amplifier, and integral operation is by integrator, right. So, we have a integrator, we can have a gain amplifier, and we can further design the Smith trigger, which is consider the registers as shown in figure. The first op amp is for setting P gain, right, which is and the second op amp is used to set the integral gain. So, the first op amp is used for proportional gain, the second op amp is for integral gain. The addition of two outputs are carried using the third op amp. So, you can see this is a proportional gain, right, this is the integral gain, and the addition of both is sent to this third op amp, right. Let us say op amp number 3, right, addition of proportional integral output, and to meet the requirement of the plant, the fourth op amp will be used to attenuate. So, this fourth op amp is used to attenuate. We can say this is 1, 2, 3 and 4, all right. So, the proportional gain is 1. Now, you can see 100 is 1, right. The integral gain of system is VO2 error by error. So, 1 by R3 into C1, which is 1 by 100. So, the overall gain is VO by VO3, correct. The overall gain is VO by VO3, and it is nothing but R7 by R8, which is 10 by 100, which is equal to 0.1, right. So, now what we have is, if we can design the proportional controller, if we can design the integral controller, and if we have the third op amp, which is the addition of both, and 4 op amp to attenuate the signal, then we can design on off controller using on off and using operation amplifier, temperature controller using operation amplifier, and it uses on off circuit, and it also uses proportional controller as well as integral controller, right. So, what we have seen here is how to design this particular circuit in terms of, we have divided in terms of blocks. So, it is not so difficult when you actually see how you can design or build a temperature controller signal conditioning system. All right. So, that is for this particular module, and in the next module let us see the entire circuit, how we can design, what kind of signals you can generate at the output of every stage, and we will see how the controlling temperature of a plant in a real time, right. So, these are all the actual or practical applications of operational amplifier, right. Till then you just look at these slides, and I will see you in the next class. Bye.